Okay, hopefully everybody's having a great morning. I hope everybody got the quiz done. I know that quiz was a little more challenging than other quizzes, but if you have any questions about it, come let me know and I can go through any of the problems that were on that quiz. Today, I'm hoping to be a slightly shorter day. Today's going to help with obviously the last section on the homework, but I think it also should help with sections 1 and 2, those homework problems where you're talking about Riemann sums and all that jazz. Okay, so let's get into it. There's only one announcement today, and that's there's homework due Monday. If you need any help with the homework, please come in. As a reminder, I scratched the first problem on the homework because, again, it's something that I touched on last semester, for those of you who had me last semester, but I didn't really talk about it this semester. So the first problem on the homework is scratched, but the rest are all still fair game, okay? And I have an office hours tomorrow, Friday, and those are on Zoom. So use the same Zoom room that you use to log in. By the way, I always have the Zoom room open during my office hours. So if you ever can't physically be in my office hours, you can always just call into Zoom and still get help on any questions. Okay, so any questions for me right now? Oh, one more thing, if ever you can't make it to my office hours for whatever reason, and you want to schedule a meeting with me, I'll send the link out in an announcement, but there's a link that you can go to actually schedule a 30-minute meeting with me where I'm guaranteed to be free. Okay, so I'll put that link in an announcement today after class. Okay, and no quizzes after class. All right, I think I saw some clapping, but all right, so here we go. So today we're going to talk about the area between curves. All right, so we know that we arrived at that definition of the definite integral by looking at the area under a closed curve, or sorry, under a smooth curve, right? We looked at this drawing about 1,000 times, where we want to find this area. That is, by definition, the integral from a to b of f of x with respect to x, right? And how did we find this area? What did we do at the very beginning when we didn't know what to do? Exactly. We took this thing that we didn't know how to do, and we said, okay, first let's try approximating. And again, everything in calculus, you get there by first starting with an approximation and then taking a limit. Okay, so first we said, well, instead of finding this, let me find the area of these rectangles. Because a rectangle has a very easy area, right? So if this is x, let me zoom in on that one right there. If this is xi minus 1, and this is, actually I've been using k's, I think. So let me change this to xk minus 1. And this is xk, then that means this height right here is f of xk minus 1. And this height right here is f of xk. And so the area of that rectangle, that one rectangle that I zoomed in on, is just the length of that base times the height, right? Well, you can actually take the height to be many different things, right? But the length of the base is clearly just xk minus xk minus 1. That's the length of the base. And for us, we're always taking those steps, the bases of all of these rectangles to be the same length, right? We're calling all of these things delta x. Okay. And so if I have an interval of length b minus a, then delta x is b minus a divided by however many rectangles I'm using. So that is n, right? In general. And then the only other thing I need is the height of the rectangle. Well, the height, I could take the height to be, I could use the left side of that rectangle. I could use the right side of that rectangle as the height. So either f of xk minus 1, f of xk, or I could take any point in between those, right? So the height I can just say is f of xk for now, and the future I'm going to say f of xk star, where f of xk star really just means instead of only picking the left or the right, I'm going to use some point in between xk minus 1 and xk. Okay. On the homework in section 1, they talk about the left endpoint. So there you're using xk minus 1 is xk star. If you're using the right endpoint, then xk star is just xk. So the area of this one general rectangle there in the middle is f of xk star, just the height of that rectangle, times delta x. That's the area of the general rectangle. And so then to find the approximate area, I take a sum, right? I take the sum k equals 1 to n. So then what we do is we take a limit. We say then that the integral from a to b of f of x, well, it's approximately this thing for any fixed n, but then when I let n get larger and larger and larger and larger, then, or in other words, I use more and more and more rectangles, then it becomes exact. And I get that the definition of the integral is this. The limit, don't forget the limit, because that's the important part, Chase. The limit as n goes to infinity of the sum k equals 1 to n of f of xk star times delta x. And again, xk star, before we were taking it to be any point, or sorry, before we were taking it to be either the left endpoint or the right endpoint, but now it can be really any point between those two. Okay. We're going to be doing a lot of things in this class where we use this idea. Instead of trying to find the answer to one big problem that we don't know how to do, we're going to say, what happens with one little sliver? What happens with one little rectangle? What happens when I take that rectangle and I spin it around? What happens when I take one little bit? Then you add them all up, then you take a limit. Okay. So this is why I walk through this again, because this process is very general, really. This is one specific application of this process. Okay. So you can use the definite integral to find more general areas than that, though, than just the area underneath one curve between that curve and the x-axis. We can actually find the area bounded by two curves. Okay, so for instance, we can find the area between the curves y equals x and y equals x squared. In other words, this area right here. And there's a couple of ways to do this. Let's discover who can think of one way to find the area between those two curves.
Find the integral of the top line minus the integral of the bottom line.
Exactly. That's technically what I'm going to go through this derivation again of cutting it up into rectangles. But really, ultimately, it's not that hard to see, right, that if you take the area under, if you take the area under, let me make that a little smaller, the straight line, which is just that triangle, right, the area of that triangle, and then subtract off the area underneath the parabola, well, then what's left, the green minus the blue, is the area we want, right? So we can really jump ahead and say, if you want to find the area between two curves, one being on top of the other, or in other words, if the top line is y equals f of x, the bottom line is y equals g of x, then the area between the two curves is just the integral of f of x minus g of x. Okay, so we can really just say that the integral here from 0 to 1 of x minus x squared dx, that gives this area. Okay. Why is it the integral from 0 to 1? I mean, we're finding the area bounded by those two curves. So why is it the area from 0 to 1? Or the integral, sorry, from 0 to 1. Exactly right. In general, I only drew parts of this curve, right? Really, y equals x squared goes off this way too. And y equals x also continues on. But when I say the area bounded by these two curves, I mean the area that's literally bounded. There's a bunch of areas happening here. There's this area, but that area is unbounded. It goes off to infinity, right? Same way with this area. That area goes off. This area goes off to infinity. There's only one area, one region here that has a finite area. Okay. So that's why I take the integral from 0 to 1, because that's where those curves intersect. Okay. All right, so if we want to find this area then, well, how do I do that? We know how to do this integral. We can break this up, right? So what's the integral of x with respect to x?
1.
Careful, wrong way.
2 x squared over 2.
Yeah, perfect. X squared, you add 1 to the exponent, and then divide by that new exponent, right? Very good. Then minus, what's the integral of x squared with respect to x? X cubed over 3, very good. So then I just plug in x equals 1, x equals 0. And when I do that, well, when I plug in 0, pretty clearly I get 0. So I just look at when I plug in 1, I get 1/2 minus 1/3, which is 3 minus 2 is 1 over 6. Okay. So all the problems I do today, for the most part, really boil down to this. Take the integral of top line minus bottom line. There are a few hiccups that we're going to talk about, but for today, this is really as complicated as it gets. Okay. So there was the idea of, if I want to find the area between two curves, take the area under the top curve minus the area of the bottom curve. That's perfectly fine. That's the way I want you to think about these problems. But like I said, I'm going to show you how to get this using rectangles again, so that you can see how this process generalizes. Okay, so let's look at a sketch again of a couple of general functions. This is y equals f of x, and here is y equals g of x. There's A, there's B. Okay, I want to find the area between these two curves. Okay. So let's pretend for a second we don't know about the definite integral. We don't know about the fundamental theorem of calculus, and we're just tasked with finding this area. What would you do? Well, what did we do before? Before we knew about the definite integral, we said that's too hard. Let me do an easier problem. And what was the easier problem? Approximating with rectangles. Exactly right. I said this curvy thing, I don't know how to find the area of that. I do know how to find the area of a rectangle. So the idea is exactly the same. We're still using rectangles, but now instead of rectangles that start at the x-axis and go up to there, now I'm just going to break this up into rectangles that go between f of x and g of x. Okay. But the process is exactly the same. I'm going to take all these rectangles to have the same width. I'm going to take all these rectangles to have the same width. So let me zoom in on this rectangle. This rectangle, we'll say, has a left endpoint of xk minus 1 and a right endpoint of xk. Okay. So if I want to find the area of this rectangle, because remember, curvy, hard. Rectangles, easy. So instead of finding the area of the curvy thing, let's find the area of a rectangle. So if I want to find the area of this rectangle, the only other thing I need, I have its base, right? Just delta x. The only other thing I need is its height. So what is the height of that rectangle, of this rectangle that I'm zoomed in on? I'll color with red to make a distinction.
Be the f of x like at xk.
Perfect.
F of x or g of x.
Exactly right. Yeah. So it was said in class, it's going to be f of xk minus g of xk, right? It's just the top minus the bottom. And in general, just like before, we could actually use the way I've drawn it. It looks like I'm using probably right endpoints, but really I could have drawn it where I took any point in between here to touch the bottom curve and the top curve, right? I really could have chosen any old point, xk star, to touch the bottom and the top. So let me draw this so that it actually touches the top there. So then that height, so the width is delta x, which is xk minus 1. The height, you're exactly right, is f of xk. If you're using right endpoints, then it's just f of xk. If you're using left endpoints, it's f of xk minus 1. And so in general, you can just write f of xk star to be any old point between those two. Minus g of xk star. Does everybody understand where that minus g of xk star comes from? Because we want that, oh, that was so awful. We want this height there. Well, that's just how high up does that top curve go minus how high up does the bottom curve go. All right. So then the area of that one rectangle is just its width times its height, right? Well, that's just f of xk star minus minus g of xk star times delta x. So then, because I've kept everything really general, I zoomed in on one general rectangle. I've been using k's this whole time. Now I can say the area of, or the sum of these areas is, well, I can just put a sum out here. Sum k equals 1 to n. So that's my approximation. How do I make it exact? Yeah, take the limit as n goes to infinity. Let the number of rectangles blow up. Really, in calculus, there's really one new idea, really at the heart of it, and that's the limit. Okay, and so in anything in calculus, if you're not somewhere even implicitly taking a limit, you might want to rethink what you're doing. But here, to give me the exact answer, I take the limit as n goes to infinity. And now here, this is gonna help a little bit, I think, on homework section 2 specifically. Now we need to recognize this as something. What does this look like? Have I seen something close to that before? A limit of a big sum of some stuff times delta x. Well, let's look back for a second. It kind of looks like this, right? Only instead of just f of x k star, I have f of x k star minus g of x k star. But that's fine. If this limit as n goes to infinity of that sum of f of x k star minus, f of x k star times delta x gives me the integral from a to b of f of x, then the limit as n goes to infinity of f of x k star minus g of x k star times delta x, well, this is just, by definition, the integral from, I'm starting at a, going to b. Now, this thing here is the function that I'm taking the integral of, right? This is f of x minus g of x. And then the delta x turns into dx, right? Which we knew, I mean, we knew that was the answer, right? We knew to find the area under that curve, one way to do it is find the area under the top minus the area under the bottom. And we know how to do that with the integral already, but now we were sort of just imagining how to get there. Okay, so ultimately, this is the takeaway for today. The area between two curves where f of x is the top curve, g of x is the bottom curve. The area between those curves is this integral. Okay. But this process it comes up on the homework, recognizing something as the integral of some function. Okay. Questions?
So if we were given a value, say it was like 2 to 3 or something like that,
Yeah.
would we just plug in, 2 as the lower limit and 3 as the upper limit, and then
yeah, absolutely.
find that
Sorry, go for it.
rectangular point? Yeah, find like the rectangular point for Riemann sum.
Yeah. If you're doing the Riemann sum, then delta x, because we're taking all the all the step sizes to be the same, you take delta x always to be b minus a over the number of rectangles you're using. And then you just plug into this. Yeah. So depending on what xk star is, in the homework, you're using left endpoints or right endpoints. So xk star is just xk minus 1. And in general, that means that you're using, I mean, xk is really, for us, your starting point, x0. So if you were starting at 2, going to 3, then x0 would be 2. And then xk is when you've taken k steps away. So plus k times delta x. Okay. Does that help? Did that answer your question? Okay, good. All right, so that's it. That's all we're learning today. So So that showed that the area between y equals f of x and y equals g of x. Again, if f of x is bigger than g of x between a and b, then that area is given by the integral from a to b of f of x minus g of x dx. Question. All right, yeah, let's look at a problem then. Find the area bounded by the graphs of the function y equals, or sorry, f of x equals x and g of x equals x to the fifth. And I did not give you a graph here. So let's get a quick graph going on. So y equals x is a really easy one. What does y equal x look like? What does y equals x look like? You can describe it in words if you want. Or even draw it in the air. Yeah, Mark got it. It's just a diagonal line, right? This is y equals x. It goes through the origin clearly. Y equals x. Now y equals x to the fifth. Who knows what that looks like? You can always plot it in Desmos. If you don't know, Desmos. Y equals x to the fifth. It just mostly looks like y equals x cubed. It's a little flatter. Bless you. A little flatter near the origin, right? So that's what y equals x to the fifth looks like. So y equals x to the fifth looks like that, only without the little bump. Here's y equals x to the fifth. So I should have added, I only want this for x between, or x greater than 0. I forgot to add that part. Because if I didn't add that, then the area would be 0. This positive area would cancel with this negative area. So we're going to forget about that negative area. Okay, and we're only going to zoom in on that part of the graph. Okay. So this is y equals x to the fifth. A rough sketch. So then what's the area between those two things? How do I find the area?
Integral of f of x.
Good. So what is f of x for us?
It's just x.
It's just x. F of x, always take the integral of the top curve minus the bottom curve. I guarantee, I did this 1,000 times when I was learning, that you're going to get them mixed up at some point and get a negative answer and think, oh, I just mixed them up and so I can just take a negative. You need to be careful because maybe they switch, maybe you mess something else up. But if you do bottom minus the top, you're going to get a negative answer where you should always get a positive answer here because we're talking about true areas. So the integral, I want x minus, because x is the top curve, y equals x, x minus x to the fifth. Now, what are the bounds on this? They're where they intersect, right? So clearly, where there's one kind of easy point that we can say, what's the easy point where they intersect?
0.
X equals 0, right? At x equals 0, 0 is equal to 0 to the fifth, right? How can I find the other point where they intersect?
When both are equal.
Yeah, exactly. With the intersection, that's just where x to the fifth is equal to x, right? So I need to solve the equation x to the 5th equals x. Now, there's a couple of ways to solve this equation. The most kosher way, I guess, I'll say, is to subtract x. Well, first, what does everyone want to do? Someone tell me what you want to do with that top line.
Wait, what'd you ask?
With the very first line, factoring is the safe way. I agree with that. Does anyone want to do something else with that first line? And if you do, it's fine. I hope someone shouts out.
Isn't it take like the 5th root or something like that?
Well, if you take the 5th root, then that would get rid of this 5 over this x to the 5, but that would put an x to the 1/5 over there. And so we're essentially in the same position. Yeah, so one thing a lot of people want to do is they can say, oh, I can cancel an x. If I cancel an x, then I get x to the 4th is equal to 1. And then x is really plus or minus 1. Now, you need to be careful. And why do you need to be careful? If you just divide by x. For us, it's actually fine because we already took care of something.
Oh, you moved it 0.
Exactly. If you didn't know what these graphs looked like, and you just went to find where they intersected, and you did this, you would completely throw out x equals 0, which is the important lower bound for us. Okay, so you need to be careful. We've already taken care of that. We already found that x equals 0 is a solution. And so then we can just say, okay, well, then x equals 1 is the other solution because I only care about x positive. But yeah, if you started out and you didn't know x equals 0 as a solution, then by dividing by x, you're throwing out that solution essentially. Okay, so you need to be careful. All right, but then we're here. This is it. All right, so what's the integral from 0 to 1 of x minus x to the 5th? Well, again, I can break that up. Integral from 0 to 1 of x dx minus the integral from 0 to 1 of x to the 5th dx. Okay, what's the integral from 0 to 1 of x? Or how do I find it?
Be x squared divided by 2.
X squared divided by 2. Perfect. And what's an antiderivative of x to the 5th? Perfect. X to the 6th over 6. And then I just plug in x equals 1 and x equals 0. Wonderful. All right, and so I'm going to get 1/2. This is equal to 1/2 minus 1/6. And then when I plug in 0, I just get a bunch of zeros, right? And so this is equal to 1/2 minus 1/6, which is what? 3 minus 1 is 2. 3 minus 1 is 2 over 6 is 1/3. Common denominator and all that jazz. Do we have any questions on that? Again, the functions can get a little more complicated, but at the heart of it, this is always how these problems go. Find out what curve is on top, find out what curve, I mean, you don't really need to do any finding out after you find out what curve is on top, the other curve is on bottom. Take the difference and integrate. Okay. So this one, I'm going to come back to if I have time. It's a fun one, but I want to make sure I tackle one more thing. So, so far I've only talked about what happens when f of x is always bigger than g of x, but it could happen that we have the top curve does something like this and the bottom curve does something like this, right? If we have, we'll call this A, and we'll call this B. You could have something like this, right? Sines and cosines do this. They switch back and forth between each other. I could still want to find the area between these two. And again, when I say the area bounded by these curves, I don't mean the signed area. I mean the actual, like viewing this as a shape, what is its area? So that needs to be positive. So how would I do that? If I had something like this, if this is f of x, and this is y equals f of x, and this is y equals g of x here. And this point of intersection here, I'll call C, x equals C. Then how would I find the area between these two curves?
The integral from a to c
Ah,
f of x minus g of x.
good. So that gives me that area. Then what? You can tell me what comes next.
From C to B, no.
Perfect, exactly right. Plus the integral from C to B. Then they flip, right? The integral from C to B of g of x minus f of x. That's exactly right. Then that gives me the blue area here. Perfect. So I'll underline that with a blue and that with a red. Perfect, guys. That's exactly right. And that, I mean, that's the hardest these are going to get. They're going to, so sometimes they switch. Sometimes they switch which one's on top, which one's on bottom. But this is all you need to do. Find out where they switch and just break the integral up. Yeah.
In Calc 1, didn't we do something where that top integral on the left, bottom right one, we can like combine them or something?
Careful, you're right, but that's if they, and I'm actually about to do that, but that's if the integrand is the same thing, right? Here, the integrand is, they switch. That's an excellent observation though, and you're exactly right. If this was exactly the same as that, then I could just combine them. And there's a way we can say, that we can simplify this that involves the absolute value function. This, just taking the absolute value of f of x minus g of x, is a short way to write what we just wrote. But I'd actually rather you guys think of it as this is the top curve and it switches at C and break it up. Because that's actually what you have to do to evaluate that anyway. Yeah. Very good. All right, so let's look at a problem like this. Find the area between the curves f of x equals sine of 2x and g of x equals cosine of x between x equals 0 and x equals pi over 2. Okay, I have some curves here. They are these curves that we're looking at, but which one's which? What is this curve here?
Cosine.
That's the cosine, very good. One way to know that it's cosine is at x equals 0, it's 1. And cosine of 0 is 1, whereas sine of 0 is 0. So this is y equals cosine of x. That makes this guy y equals the sine of 2x. Okay. The other way to notice the difference is the sine of 2x is going to be squished horizontally, right? That 2x squishes that curve horizontally. Okay, so the only thing I need to know then, just like before, this integral, or sorry, this region, I'll call it region 1. To find that, I'm going to take the integral of what? What's the top curve for that region 1? Cosine, yeah. So I'm going to take cosine of x minus sine of 2x dx. in that first region, which clearly starts at x equals 0 and ends somewhere. So we need to find this point of intersection here, right? So how do I find that point of intersection? Exactly right. We're going to set sine of 2x equal to cosine of x. And this is actually not super easy to solve just looking at it. If that was just sine of x, it would be really easy to solve because then it's just pi over 4, right? But sine of 2x, well, I don't know how to handle that. So the way you handle sine of 2x, I'm telling you now, if you ever see a sine of 2x and you want to solve an equation like this, you use the equality sine, or the identity sine of 2x. This is equal to 2 times sine of x. Oops, sorry. Let me move this. 2 times sine of x times cosine of x. Okay. All right. So then I'm going to replace that right here. And by the way, on an exam, if something like this comes up, I'll definitely give you this identity. I don't care. There's only one trig identity that I really care that you memorize right now. Later, there will be a few more, but this isn't one of them. Okay. So I plug that in here. I'm going to get 2 times the sine of x times cosine of x on the left is equal to the cosine of x on the right. So now to be safe, I'm going to subtract cosine of x over. I get 2 times the sine of x times the cosine of x minus cosine of x is equal to 0. And now what can I do on the left there? What do both of those terms have in common?
You want to factor?
Perfect, exactly right. I want to factor out cosine of x. I'm left with 2 sine of x minus 1 equals 0. So either cosine of x equals 0, which happens at pi over 2, which we can see that already, right? We can see that right there, that those two equal each other at pi over 2. Or 2 times the sine of x minus 1 equals 0. 2 times the sine of x minus 1 equals 0, which is the same thing as saying if I add 1, 2 times sine of x is equal to 1, sine of x is equal to 1/2. So who knows where the sine of x is equal to 1/2? Perfect, 30 degrees, which is in radians, pi over 6. Perfect. That's exactly right. All right, and then from there, the rest is gravy. I don't know. The rest is pretty much plug and chug. How do I find the area of region 2?
You're going to use the upper bound as the lower bound for area 2.
Perfect.
And
So
then
I'm-
switch the function.
Exactly right. Then I switch the, because now in region 2, sine of 2x is on top, right? So I'm going to get sine of 2x minus cosine of x dx. And then the upper bound, well, I actually gave you up here, you care about this between x equals 0 and x equals pi over 2. And so you know that that final upper bound has to be pi over 2. Okay. So we can go through and find this. I do want to show you something that you're not going to be allowed to use on exams, but, and some of you might know this already, but I want you to be able to check your work easily. So in Desmos, you can come into Desmos and type INT get an integral sign. And then you can integrate from 0 to pi. Let's look at pi over 6 first. 0 to pi over 6 of cosine of x minus the sine of 2x dx. Where's x? X. There we go. And Desmos, if you have a sum or difference of something like this, you need to put it in parentheses for Desmos to actually want to do it. And you get 1/4, 0.25. Okay. So do these by hand. If you don't know how to do an integral on the homework, you're not going to know how to do it on the exam. So do these by hand, but feel free to use Desmos as a check. Okay. In real life, you're going to get to use a tool like Desmos to check your work when you at your job, right? So feel free to use Desmos as a check when you've done everything by hand. Okay. So the area of the region 1 is 0.25, and I'll let you guys find the area of region 2 on your own before moving on to this different example. And this, I just want to mention this example because next week we're going to pick up with something that looks like this. This one's a little different, right? So let's consider finding the area bounded by the curves given by the functions f of x is x squared, g of x is 2 minus x, and h of x is 0. So this almost triangular region in here. Okay. So now looking at this, is there a top curve and a bottom curve? No, right? The top curve, really the only way to think about it is you have to break up this region into 2 pieces, right? This is region 1 now, and this is region 2, right? And so how would you find the area then? Still an area, so it's still going to be an integral, but let's just zoom in on region 1. How do you find the area under that parabola, y equals x squared?
You get an integral from 0 to wherever they intersect.
Perfect. And for here, and to be quick, they intersect at 1, but to find that, you just set them equal to each other, right? From 0 to 1, and then what do I put inside the integral?
Just be x squared.
X squared, perfect. X squared. And technically, by the way, it's x squared minus 0, right? Just the definite integral is really finding the area between 2 curves where the bottom curve is g of x equals 0. So x squared dx. Very good. So that's region 1 plus the area of region 2. Well, I mean, it's the same thing. It's I'm finding an area, so I'm going to do an integral of this. Now it's under this curve, right? Which is 2 minus x. And the bounds are going to be 1 to 2. So for this problem here, it seems like you have to break it up. We're going to see on Monday that there's actually an easier way to do this, as well, easier is maybe relative. But there's a way to do this involved using only one integral, where instead of thinking of the top curve minus the bottom curve, here you would think of the right curve minus the left curve. Okay, so we're going to translate this area into, really, we're going to switch from x's to y's, and then we can find this area using one integral instead of breaking it up into 2 integrals. Okay, so that's what we're going to be doing on Monday. I believe you have everything you need to be able to do the homework now. If you run into any problems, please email me or Zoom call me or whatever, and I'll be more than willing to help. Okay, so just make sure to get the homework done, do Monday night, and then I will see everybody on Monday. Have a great Friday, Saturday, and Sunday. Thank you all for being here.
Thank you.
Thank you.